And welcome back. So we're going to continue looking at our topic on structure and bonding by having a look at the continuum of bonding type. Now I very much doubt you know what this means at this point. It's certainly not a commonly used term, and thankfully you won't have to write this in any of your answers, but you do need to know what it means. So learning targets for this video are to be able to define a key term in electronegativity, be able to recall the trends in electronegativity as you go across a period or up and down a group, and you should be able to work out the type of bonding based on differences in electronegativity. So at GCSE you looked at 3 types of distinct bonding. If there were 2 metal elements, you had metallic bonding. If there was 1 metal and 1 non-metal, you had ionic. And if there were 2 non-metal elements, you had covalent bonding. And they were very separate and distinct. And unfortunately, that isn't quite the case. Okay? So we're not going to be looking at metallic bonding today, but we are going to discuss the difference between ionic and covalent. So these are 2 representations that you should hopefully recognize. You have a molecule of chlorine, which is covalently bonded, and you have sodium chloride, which is ionically bonded. Now, you learned a covalent bond is a shared pair of electrons in between the 2 atoms. So let's just put in those 2 electrons. Now, you might not have considered it before, but at GCSE, you sort of assume those electrons are in the middle of the bond. They're either shared, like in the left-hand side example, or the electrons have gone all the way to one side, which is what ionic bonding is. It's the transfer of electrons. Now, as I said, at GCSE, you kept these 2 types of bonding quite discrete, quite separate, but it's not quite that simple. For instance, if you have a carbon-chlorine bond, the electrons are not exactly in the middle. They're actually closer to the chlorine. They're not all the way over. This is not an ionic bond, but they're not exactly in the middle either. This is what we call a polar covalent bond. And this is because, much like a magnet or the Earth, this type of bond has poles. Because the chlorine has slightly more electron density than the carbon, it is termed delta negative. And because the carbon has lost some of its electron density, it has a lower amount of electron density, we say it's delta positive. This is a polar covalent bond. Now, how do you know if a bond is polar or not? Well, that is to do with something called electronegativity. So, definition first. Electronegativity is the ability of an element to attract the shared pair of electrons in a covalent bond. So the closer the electrons will go to one element rather than the other, the more electronegative it is. So in a chemical bond, you can kind of think of it as a tug of war. So the 2 atoms are both trying to attract the electrons towards themselves, and the stronger one, the more electronegative one, will get the electrons closer to it. So in the example we looked at, the chlorine is more electronegative because it is better at attracting those electrons towards itself. So here's a picture of the periodic table with all of the electronegativities written in. Now, if you search for electronegativities online, you will actually get different values depending on which electronegativity values you use. This is the more common one. It's called the Pauli electronegativity values. Okay. Now, you will not have to memorize any of these numbers, but you should be aware of the trends so that you can determine whether a bond is polar or not, whether a bond is perfectly covalent, polar covalent, or ionic. So, general trends you need to know about. Now, the transition metals in the middle, they don't necessarily follow the trends you need to know about, so don't worry too much about those. But other than that, there are two distinct trends. Now, electronegativity is determined by two main factors. The nuclear charge of the nucleus. The bigger this is, the greater the attraction to the electrons in the shared pair, so the more electronegative it is. And also the size of the atom. The smaller it is, the closer the shared pair is to the nucleus, hence the greater the attraction. So as you go across a period, not only does the nuclear charge increase, but the size decreases. Therefore, electronegativity increases. And also as you go up a group, because the elements are getting smaller, again, electronegativity increases. So again, ignore the transition metals, but if you look at the other groups, you can see that this is the case. So the most electronegative element on the periodic table is fluorine in the top right-hand corner, and the least electronegative is francium. Now you'll notice that these three noble gases don't have a value. That's because they don't form covalent bonds, so they don't fit in for definition. So I know there are elements further right and further up than fluorine, but fluorine is the most electronegative. So how do you determine the type of bonding from these values? So I've drawn a diagram here to try and help you understand. Now, to determine what type of chemical bond you have to work out the difference in electronegativities between the two elements. So use these values, take the biggest away from the smallest, and the value you have determines what type of bond it is. So if you have a value from 1.7 and above, this will give you an ionic bond. Now if you have a value of 0, it's a perfectly covalent bond. But even if you go up to about 0.3, the difference is small enough to term this a non-polar covalent bond. The electrons are still pretty much in the middle. They haven't moved far enough to give you positive and negative partial charges. And then in between the two values gives you polar covalent bonds. You still have covalent bonds, they're still shared electrons, but they are significantly closer to one atom than the other. Hence, you would give that bond partial charges, classes as a polar covalent bond. So let's just look at a few examples. So let's look at sodium and chlorine, your typical example of an ionic bond. So these are two electronegativity values for sodium and chlorine. Sodium is 0.93, chlorine 3.16. Take the small one away from the big one, and it gives you a value of 2.23. 2.23 is in the ionic bonding section. Although you can see it's actually quite away from the most ionic substance you can get. So next, let's have a look at carbon attached to a chlorine, like we looked at in the previous example. So carbon, the value of 2.55. Chlorine, 3.16. Gives you a value of 0.61. 0.61 is a polar covalent bond. The electrons are more towards the more electronegative of the elements, which in this case is chlorine. Okay, so in a previous video, I mentioned how aluminium chloride doesn't fit with your GCSE definitions of bonding. So let's have a look at that one. So aluminium is the value of 1.61. Using chlorine here, which you know is 3.16. So for this bond, you have a difference of 1.55. So you can see here that despite the fact that it's a metal and a non-metal, we actually have a value which fits in with a polar covalent bond. And one more example. Let's have a look at a carbon-hydrogen bond, because we'll be doing a lot of this in the organic chemistry section. So carbon is 2.55, And hydrogen is 2.20. Now this gives us a value of 0.35. Now this is just on boundary between non-polar covalent and polar covalent. But at A level, we consider this to be a non-polar covalent bond. Okay, the electronegativity difference is small enough for us to consider it as a non-polar covalent bond. That's important when we go into other topics. Okay, so quite a lot of new theory there, but the things I want you to take away from it: you need to be able to define electronegativity. Make sure you add this to your glossary. You need to know the trends in electronegativity from the periodic table. And you should be able to work out the type of bonding due to the differences in electronegativity. So if you still don't understand some of this, make sure you write down your questions so that you can ask me about it when I see you in class.